Hello, welcome back to this course on discrete mathematics, and I am Professor Anand Paul, who are lecturing this course here online. And as we have seen different parts of logic of compound statement, and this is the last section of this logic of compound section, part 4. And today we are going to discuss about certain principles that supports the statement of logics. So the first part is about modus ponens. So basic idea behind the modus ponens is that let's start with an example and see how it works. So say for example we are given with the two statements. You are in the class. If you are in the class, you will get the grade. So let P equals you are in the class, and let Q equals you will get a grade. So this is what modus ponens states. Given P, P implies Q. Therefore, it's Q. In other words, when P is given, you can conclude Q. So what does it mean? So by modus ponens method, you can conclude that you will get a grade. Let's think about it. If you are in the class, then you will get a grade. That's what the modus ponens talks about, because P is you are in the class. If that is true, then the conclusion is also true, that you will get the grade. To understand further, let's talk about this. So this modus ponens is the inference that if one statement or proposition implies a second one, and the first statement or the proposition is true, then the second one is also true. That is, if P implies Q and P is true, then Q is true. It is one of the very basic common concept that is used in logics. Given P is true, you can make a conclusion. For example, if it's raining, I will meet you at the movie theater. It's raining, therefore I will meet you at the movie theater. As modus ponens can be stated as given P, P implies Q, therefore Q. So on the reverse is not true. Just to understand, when P is true, then Q is true, but the reverse, if Q is true, P not necessarily true. So don't get confused with it. So this modus ponens is the logic used for affirming that whenever P is true, Q is true. So this is like equivalent to P and P implies Q implies Q. Can you see there? The P implies Q is there, but the P has to be true. Only if P is true, then this whole part implies Q. Here it is, the truth table that can give us some idea. So this is where we come across when P is true, then P implies Q is there. In other words, given P is true and P implies Q, therefore Q is true. So we are focusing on Q. That is what is all about. The consequent, the conclusion. So that's the modus ponens. So assume that you know negation of Q, and P implies Q. So when I say assume that we know negation of Q, which means that if given with the negation of Q to be true and P implies Q, you can also recall P implies Q is equal to negation of Q implies negation of Q. Can you recall that? Yes, that is the conditional statement P equals Q, that is equal to the contrapositive, which is negation of Q implies negation of P. So thus we have a negation of Q, and negation of Q implies negation of P. So that's from the contrapositive. Therefore we can conclude that negation of P. How do we express it? Therefore modus tollens can be expressed as follows: negation of P, which is given to us to be true. In that case, if P implies Q, then therefore we can conclude that negation of Q. When negation of Q is given, we can conclude that negation of P. So this part is the negation of Q is given to us, P implies Q, therefore negation of P. Just to clarify that. So let's assume these two sentences. You will not get a grade. If you are in the class, you will get a grade. So let P be you are in the class and Q is you will get a grade. Let's talk about here. Negation of Q is given. So when P implies Q, what conclusion we are to make? Negation of P. So in that case, negation of Q is you are not getting a grade, and the conclusion is that you are not in the class. Yeah, that's the output of modus tollens. In other words, here is a simple and clear definition for this modus tollens. So it is the inference that if P implies Q and Q is not true, then P cannot be true. It is closely related to one another valid form of argument, the modus ponens. We just talked about modus ponens. So this modus tollens is very closely related to this argument of modus ponens. So they are also quite similar, but invalid arguments such as affirming the consequent and denying the antecedent. As the rules says as such, negation of Q is given to us, therefore we can conclude the negation of P. So those are the examples we have seen. You can also think about other example. If P is sky is blue, and if Q is it is not raining, now what would be negation of Q? It is raining is negation of Q, and what you can conclude? Negation of P, which means sky is not blue. Probably it might be cloudy. Anyway, just for your understanding, I am giving those examples. So the basic idea is simple. That's the expression of contrapositive. Generalization and specialization. So we will come across this again later on in our coming lectures, how to express these terms. But this gives you the very basic of what a generalization means and what a specialization means. Coming to generalization, if you know that P is true, then P or Q is always be true. So given P as true, therefore you can say that P or Q is always true. So that's a basic generalization. Specialization is that if P and Q is true, then P will always be true. Yeah, that's quite obvious because it's an AND operation. So given that P and Q is true, therefore we can conclude that P is true. Let's have some more information about this example with proof. So we have the hypothesis, it is not sunny this afternoon and it is colder than yesterday. We will go swimming only if it is sunny. If we do not go swimming, then we will take a canoe trip. If we take a canoe trip, then we have to be home by sunset. Let's try to put some symbols for these statements. Okay, the question is, does it imply that we will be home by sunset? So that's the question asked. Let's see whether we were able to make such conclusions. Okay, the font has been changed, but it's the same sentence that we have seen earlier. Same sentence is there. Just a color expression has been used here for us. So it is not sunny this afternoon and it is colder than yesterday. So let's take it as P. P is it is not sunny this afternoon. P is it's sunny this afternoon. Q is it is colder than yesterday. R is we will go swimming. S is we take canoe trip. T is we will be home by sunset. So we have to check whether we can make such conclusions. So negation of P and Q, which is it is not sunny this afternoon. So negation comes in because of the not, and it is colder than yesterday. That is Q. Then comes R implies P. We will go swimming only if it is sunny. R implies P. Then negation of R implies S. If we do not go swimming, the negation of R comes because of not there, then we take a canoe trip, that is S. If we take a canoe trip, then we will be home by sunset, that is T. So we have to make the conclusion that will we be home by sunset? T. So that's the problem given to us to make such conclusions. Let's see, let's use this hypothesis 1, which is negation of P and Q. Do you remember that? That is, if it is not sunny this afternoon and it is colder than yesterday, that is negation of P and Q. That is the first hypothesis given to us. Remember, these sentences are the hypothesis that is given to us, and from this hypothesis we are trying to make conclusions, and in between we are going to use some of the laws and other things that we have seen like modus ponens and modus tollens, we can use it. Here it is. So we have this form P and Q. So in this P and Q, we can conclude that if P and Q is true, we can conclude that P is going to be true always, right? So that's kind of specialization that we talked about. P has to be true in that case. So from this first hypothesis, the negation of P has been taken as simplification. For simplification, we are just taking the negation of P, assuming that the first hypothesis, negation of P and Q, is true. If that is the true one, then we can say that negation of P is true. Second hypothesis, R implies P. Can you recall what it is? We will go swimming only if it is sunny. That is R implies P, your second hypothesis. So negation of Q, if that is given to be true, P implies Q, therefore negation of P. So here we have this form where from this we can conclude that it is negation of R. Can you compare the step 2 and step 3 there? In step 2 you have negation of P to be true, and in step 3 you say that R implies P, that is equal to this part. We are just comparing that with that. Step 2 is like negation of P, and here is R implies P. Therefore the conclusions that you are going to make here is what matters for us, that is negation of, this is negation of R. So that's by means of modus tollens using step 2 and step 3. Negation of R implies yes. So that is your third hypothesis from the given statement you are coming up. And again, can you find the relation there? Yes, P implies Q, therefore it is Q. This is similar to here. What we have here is negation of R. Negation of R implies yes. Therefore, we have to make this conclusion of Q, which is going to be yes. So that is modus ponens using step 4 and step 5. Okay, now we are here in step 7, which is the fourth hypothesis, S implies T. So in 6 and 7, can you use 6 and 7 and make a conclusion? Just think for a moment and see whether you can make a conclusion. Yes, given yes, S implies T, therefore it's T. That's right, we are using modus ponens for step 6 and step 7. Same idea. So which means that given a hypothesis, given a conditions, you can actually simplify things and you can use these modus tollens, modus ponens, as well as other related things that we have learned to make a certain conclusion. So we just showed here that the given part to make a conclusion that we will be home by sunset, that is T. We used all these 4 hypotheses. So when 4 hypotheses are true, then we say that the implication is true. So in other words, we showed the above is tautology. It always remains true. So you can actually use the truth table to also show the same thing. You can generate the truth table if you like, and if you wish, you can also go through this website to see more information on generating the truth table for any given equation. So here is how you can do it for this given problem there. Let's move on. So more rules for inference is given to us for us. Conjunction. If P and Q are true separately, or if P and Q are true separate, they are separately true. In other words, P is true and Q is true separately, then P and Q is true. Yes. So when you say conjunction, you are actually combining P and Q. We say that P and Q are true separately, and now you are having a conjunction of combining P and Q, which are true separately, but when you combine these two, this becomes true as well. So that is the conjunction principle. Given P, given Q, and they are true separately, therefore we can conclude that P and Q are true. Elimination. If P or Q is true and P is false, then Q must be true. Got it? Yeah, that's a basic OR based algorithm, logic OR. So we are given with the condition that P or Q is true. You know that P or Q is true, but you know that again negation of P, or in other words P is false. If P is false, definitely Q has to be true. Well, these are some of the logics, but these logics can have a far reaching understanding for us, because as you contemplate and as you have more insight on these logics, later on you can see how these can be very useful for various fields, whether it's a basic programmings that you are going to use, or you are going to use certain state missions, or even when you are using some artificial intelligence part, we can think about certain logics. We have to do it for machine learning purpose as well at times. So these are very basic informations that you can build on later on to see how things would work, because we are trying to infer things from the given things. We want, as far as the artificial intelligence is concerned, we want certain logics, right? For example, NLP is there, natural language processing is there. We want the system to understand what we are trying to say, what we are trying to infer. Yes, does the system try to understand that? These are some of the basic principles, in fact. Well, today we talk about conjunction elimination, but there are a lot more to this. Transitivity is another one. If P implies Q is true and Q implies R is true, then P implies R must be true. So can you think of very basic things like if A equals B and B equals C, therefore A equals C. It's a very basic math. It's a very simple logic. In the same way, we have this condition. If P implies Q is true and Q implies R is true, therefore P implies R must be true as well. So there are more points on this inference. Proof by division into cases. If at least one of P or Q is true, then R must be true. So if P and Q, or P or Q is true, P implies R is true and Q implies R is true, therefore we can make conclusion that R must be true. Contradiction rules. If negation of P implies C is true, we can conclude that P via contrapositive it's true. That is, negation of P implies C, therefore it is P must be true. So that's for the contradiction part. Resolution: if P or Q is true and negation of P or is true, then in fact it's Q or must be true. That is, P or Q is true and negation of P or is true, therefore Q or must be true. These are some of the inferences. So given a hypothesis, if it does not rain or if it is not foggy, then sailing race will be held and the life-saving demonstration will go on. This is an hypothesis. If the sailing race is held, then the trophy will be awarded. Another one, hypothesis: the trophy was not awarded. Is that the conclusion? What do you make? Can we conclude that it has been rained? So you can express it in terms of symbols like negation of or, that is, it does not rain, or negation of F, if it does not foggy, implies that the sailing race will held and the life saving, that is L, will go on. And S implies T, the sailing race is held, then the trophy will be awarded. Negation: trophy is not awarded, therefore can you conclude it has been raining? So based on hypothesis 3 and 2, we can conclude that negation of Q with P implies Q, therefore we can say negation of P, that is in this case negation of S, that is using Modus Tollens rules, and using hypothesis 1 and contrapositive for step 4, we can make this conclusions. Like negation of S and L implies negation of or negation of F. So we can use the De Morgan's law and double negation rules to simplify it further. Therefore we can use this part: if P is true, then we can say that P or Q must be true as well. So that we can use it here. Addition from step 3 there. If P is true and P implies Q is true, therefore Q must be true. So modus ponens for step 6 and 7. Then P and Q is true. In that case, P should be true. Therefore, or. So that is it. We made the conclusion as or. It has rained. Let's see one more examples of knights and knives. So an island containing two types of people: knights who always tells the truth and knaves who always lies. You are visiting the island and you are approached by two natives who speak to you as follows. A says B is a knight. B says A and I are of opposite type. What are A and B? It's quite confusing because these people, we are not sure who is who, and we know that there are two types of people: the knights who always tell truth and the knaves who always lie. Let's see here. So A and B, let's suppose this A and B both are knives. So let's suppose A is a knight. We are not sure who is what, but let's suppose A is a knight. If A is a knight, then he has to tell the truth. So what A says is true, Therefore, B is a knight, right? Because A says B is a knight, so we can say if A is a knight, he says the truth, therefore B is also a knight. What B says is also true because B is a knight. And what does B says? B says A and B are of opposite type. Right now you have arrived at some kind of contradiction. A and B are both knights and A and B are of opposite type. Yes, this is a contradiction. Therefore, which means that the initial supposition is false. Initially we suppose that A is a knight. So A is not a knight. If A is not a knight, then A is a knave. If A is a knave, what A says is a false one, which means that B is not a knight. Therefore, B is a knave. So you can think back about this whole problem here, and as you think back about this whole problem, so the reasoning can be confusing at times. So A and B both must be knaves. There is only one satisfiable answers or solutions that you can come up with. In fact, the problem seems to be no solution because the problem statement could be inherently contradictory. If you look back at the solution though, you can see that it does not work out for both A and B to be knaves, because there is going to be another contradiction coming up. Here is an interesting question for you to think about. Who is the killer? Sharkey, a leader of underworld, was killed by one of his own band of 4 henchmen. Detective Sharp interviewed the men and determined that all were lying except for one. He deduced who killed Sharkey on the basis of the following statement. Shoko says that Lefty killed Sharkey. Fat says Muscles didn't kill Sharkey. Lefty says Muscles was shooting crabs with Shoko when Sharkey was knocked off. Muscles says that Lefty didn't kill Sharkey. Now the question is, who killed Sharkey? Unlike the previous one, this problem has a definite answer. The previous one we say that the problem itself is contradictory in nature, but this one, if you try to outline, try to write down step by step and use the symbolic logics and try to make a conclusion, yes, you will find that you are going to find the killer of Sharkey. Can you try it? Why not try it by yourself? I give you a chance to work it out, and later on I will also share with you some more problems we can work out for this arguments, deducting conclusions from logical arguments. So in fact we have come to the conclusion of all the parts that is related to logic of compound statement, and it's good that we have covered this in this series of lectures. And in the next lecture we are going to consider more topics of quantified statement. That's again is quite important part for us to lay foundation into the discrete mathematics. So I'm looking forward to see you there. So you can consider there are a lot of other examples of proofs that you can come up with. So we have seen Modus Tollens, Modus Ponens, and we have seen other rules that are related to the logics. For example, when a given thing is true, how we can deduce that other things can also be true. But there are certain cases in which we might fall into some trap of making the false conclusions. So just to give a brief idea of what that could be, you can look at this statements here. So here this is not a valid rule there. So when a Q is given to you, if P implies Q, therefore P. So it's like if you have the values of P implies Q, and there may be certain cases in which it might not be true. So it's like saying like we know that when P implies Q is true, we know that the negation of P implies Q is also true. But when P implies Q is true, it doesn't mean that Q implies P is true. So that's kind of fallacy of affirming conclusion. You can't make a decision based on the conclusion. If the conclusion is true, you can't just say that the hypothesis is also true. Sometimes it may not be true. So in one of the previous lecture, I gave an example like, if I am elected, I will reduce taxes. So sometimes the taxes are reduced, but I am not elected. Yeah, it doesn't mean, reducing of taxes doesn't mean that you are automatically elected. Say for example, somebody is elected and he reduces the tax. Anyway, sometimes we should be cautious of this. So that's another equivalent part called modus Badus, where we say that confirming the conclusion does not really affirms the hypothesis. For example, you will get a grade. If you are in the class, you will get a grade. Let P be you are in the class, Q is you will get a grade. So here it is, given Q, which means that you will get a grade. If that is true, P implies Q, therefore P. You cannot conclude that you are in the class, or you cannot conclude that you are in this class and you could be getting grade for other classes. That's not possible. Moreover, this statement again of fallacy of denying hypothesis, yeah. So at times it's a fallacy of denying conclusion, and here is fallacy of denying the hypothesis. Both are not applicable. We can see this example as well. So here negation of P, which is you are not, or you cannot conclude that you will not get a grade. You could be getting a grade for other classes even if you are not attending this class or you are not in this class. So anyway, this is just an example for you like how things might turn or lead you in a different path. So just be cautious that we should be making conclusion based on the logics that we have been using earlier. So this in fact concludes all things for today's lecture, and as we move on into the next part of quantified statement, we will talk about more logics there as well, and in between I will give you certain problems to solve for you guys with related to the things that we have seen in the last 3 lectures. So until then, have a nice time and goodbye.